The second part of chapter 9, of course, it is the second part in the video, but it is called part 3, Geologic Study Photo Summary. Just a reminder what we were studying in the previous part. We said that we are going to study, or we have already studied 4 categories. Geomorphic process, these are the forces shaping the earth. Then geologic structures that resulted from the shaping of the earth. Then the geologic time, to know the time scale for layers, which is younger, which is older, and so on. Then unconformity that sometimes happens to this geologic time scale. If I take a very, very deep borehole, I will find that some of the periods here are not there. Why they are not there? Because of erosion that has happened to them. Geomorphic process. One of the geomorphic process is the endogenic forces, which is the earthquakes. Of course, you have a chapter for earthquake, you have to study it, but earthquakes are a sudden motion happening because of energy being stored inside the rock, then it is suddenly released, resulting in very strong waves penetrating or going through the rock and shaking the rock and forming new, maybe forming new structures in the layers. For earthquakes, we have to know what is the focus of the earthquake, which is the point of the initiation of the earthquake, where the energy was released. The epicenter is the projection of this point on the surface of the earth. These are important things. What are the waves resulting from the earthquake? We said that we have 4 types of waves: P wave, S wave. These are category of waves, and L wave and R wave. Each one has its own shape and method of propagation. We said that to know how to locate where is the location of the earthquake, we use the P wave and the S wave, and we said that for the S wave, it cannot penetrate inside, because S wave is called, it's more or less, it depends on shear forces. So how come shear forces would propagate into liquid? They cannot propagate into liquid. So if this is the center of the earthquake, all types of waves will go, but part of the waves will be prevented from continuing when it touches the liquid part of the core of the earth. So at this location we have P wave and S wave. At this location we have P wave only and S wave was prevented. At this location we don't have any waves. Why we don't have any waves? Because the S wave was prevented and the P wave was refracted. It means that the direction of the wave, when it entered inside the liquid, it was deviated. So because of this deviation, it resulted in an area or a space where I don't have any wave, neither P wave nor S wave. So it means that if I am standing here and I cannot monitor the earthquake, it means that I'm standing in the blind zone for this earthquake. I'm not going to receive the P wave and I'm not going to receive the S wave. Here I can receive the P wave. Here I can receive both waves. This is important for those who are studying earthquake. How to locate it? This is the focus of the earthquake. This is the P wave and this is the S wave. We know that the P wave is faster than the S wave, so there is a time lag. If I'm standing at this station, then I will record the P wave first, and then after a period of time, small period of time, I will start recording the S wave. Then I will start recording other surface waves coming. But what is important for me are these P and S waves. So this time lag, I'm going to measure it. If I have this point A, if I move this point A to this point B, I will still get the P wave and the S wave, but I will have bigger time lag. It means, because the waves had to travel longer distance, it means that the time lag is directly proportional to the distance between the focus and the recording station. So if I manage to calculate this time lag, then I can know how far is my recording station from the origin of the earthquake. Here I can say that this is the distance. Here I can say that this is the other distance. So I can use this. How can I use this? Imagine that you have an earthquake and it was recorded in 3 places. One in India, the other in, say, here in Europe, and another in, say, Egypt. When I record this earthquake, I can say that the earthquake is at a distance of, say, this amount of kilometers from my recording station. So if I start with this recording station in India, the maximum they can do is that they can draw this red circle and say that there is an expected earthquake at any point on this red circle. So in Egypt, they can record also the earthquake, and they can draw this blue circle. So now in India, they have any location on this red circle. And in Egypt, they have any location around this blue circle. So the intersection between the blue and the red circle will be the combined result of both stations. It means that I don't have except 2 points, this point and this point, that are expected to be the center of the earthquake, because they are the only 2 points that satisfies the results of India and the results of Egypt. I still have an option of 2 points. Then if I have a results coming from Europe, then this result will give me this green circle. So this circle will intersect with this point. So this is the epicenter or the origin of the earthquake. So the minimum number I need to define the location of the earthquake is 3 recording stations on the earth. So this is very important. Another important thing for earthquake is how we measure it. We measure an earthquake using Richter scale or Mercalli or modified Mercalli scale, both. What is the difference between them? You can refer to this figure. This is important. What are the similarities between both? And what are the differences? The major difference between Richter scale and Mercalli scale is that Richter scale for an earthquake is 1 for the whole earth. If I say I have an earthquake with a magnitude of 3 or 4 Richter scale, it means that it is 3 or 4 anywhere on the earth. But if I have an earthquake that is 3 or 4 in Mercalli scale, it depends on where you are measuring it. Why? Because Mercalli scale judge the earthquake based on the degree of damage that it would influence on the structures and on on living human beings. So depending on what we feel from the earthquake, do I feel shaken or not, do I feel it or not, or do buildings cracks or not, buildings fall or not, these are all factors that define the Mercalli scale. But the Richter scale is the amount of energy released at the focus of the earthquake, so it is the same all over the earth. This is the most important. Of course, there are other points you have to check it, but we have said it before. Seafloor spreading. Seafloor spreading is very, very important. Of course, seafloor spreading, it is the second theory that came after the drift theory that was given by Wagner. This is important, but this is history. But seafloor spreading is another theory that help us to understand earthquakes, to understand volcanoes, to understand everything. Because what happens is that this upper layer of the crust, the thin layer below the oceans, is the thinnest layer of rock. So due to the tension happening on these layers, they may crack and they may split into 2 parts. When they split, they move to collide with other layers on the shore, the continental crust, and the gap here is filled with molten material coming from inside. So that's why the earth is increasing in size. It is increasing in size because I have new material coming to join the surface of the earth. What about this layer? When they collide with this continental crust, one of them go down, which is the smaller. Of course, the thinner will go down and the bigger will stay here. So the bigger will be bigger again. Why? Because it will result in not only being bigger, it will result in forming new mountains, increasing the thickness of the layer, volcanoes erupting and adding layers on top. So every time this thickness increases because of new material coming on top due to volcanoes, and in the same time the motion of this layer going down results in having earthquakes in many places. So that's why at the edges of the plates we always have earthquakes. So this is the seafloor spreading, and here these are the edges of the plates, and the red line is the edge of the plate, and the yellow circles are the amounts of volcanoes that the amounts of earthquakes happening. You will find that there is matching between both. Along these red lines we have yellow circles. It means that earthquakes are located at the edges of the plates because of the relative motion between them. Very important graph is the graph showing the motion of the earth. One thing you should know is that there is a background activity. It means that if I say that I don't have earthquake now, it does not mean that the earth is not shaking. It is shaking, but shaking with a very small magnitude that we cannot feel. So there is a background activity happening all of the time. The earth is always shaking, but shaking slightly. Then suddenly it starts to have increased motion. When this increased motion reaches the peak, this is called the main shock. And whatever had happened before this main shock is called the foreshocks. Then later, after the main shock, I expect that I may have aftershocks. And these aftershocks are very important because for many reasons. Structures will be affected by the main shocks. So they may be re-affected by the aftershock and fall. Maybe the main shock resulted in cracking and destroying parts of the buildings, but the building is still standing. Then when it have another aftershock, it falls and collapses. So this is one thing. The second important thing is usually after the main shock, people rush inside buildings to help others to come outside, to help injured people. So later, if a building falls due to the aftershocks, it may have more people inside. So we should know that we can expect aftershocks after the main shock of the earthquake. What are the effects of the earthquakes? The effect of earthquakes are shaking of the rock, liquefaction of loose sand, and tsunami. Let's take the two first here. Shaking. This is a very good simulation for shaking. Buildings fall because of the shaking. Liquefaction of loose sand. Loose sand have a special criteria, is that when it is affected by very, of course, loose sand that is below water table. When something like this motion happens, the shear strength of the loose sand disappears. So it turns up to be something like liquid. So if I have these buildings standing on loose sand, they were standing, but after the earthquake, you will discover that your buildings are standing on water, so they tilt and collapse. Third thing is the tsunami. Due to the here, if I have a wave here happening due to the motion of the crust here, then there will be a wave going inside the water. But here the depth is big, so the effect will not be noticed. But once this wave reaches the shallow shore, then I will find that suddenly I have a very high wave that I cannot imagine. It may be 20, 30 meters on top. So it destroys everything in front of it. Can I predict earthquakes? So far the answer is no. يعني don't believe anyone who can tell you that we can predict earthquake. We can only predict earthquake just seconds or minutes before it. How can we do this? Using what we said before. We have monitoring stations and or recording station. This recording station can tell other people after it that there is an earthquake coming to it, and this earthquake is expected to reach their location. Yani, say I have a sensor here. This sensor, he will first the P wave will arrive, then the S wave. Once the P wave and S wave arrive, then we can define the location of the earthquake, and we can tell people living here, take care, within few minutes you will have an earthquake. Of course, a few minutes is not a long time to manage to evacuate a skyscraper and so on. So it is not an early warning, it is just a little bit of warning. This was the endogenic forces. What about the exogenic forces which come from outside? We have weathering. It is either mechanical weathering, which is one of the mechanical weathering forces are the frost weathering, where water comes inside, changes into frost or freezes. When it freezes, it increases in size, pushing both sides apart and increasing the size of the gap where they were filling. Mechanical weathering, it is number two, thermal expansion. Thermal expansion is because of the effect of day and night. During the day we have hot weather, during night it is cooler, and so on. So always I have an external layer that is affected, each day affected by cold, hot, cold, hot, cold, hot. So it ends up يعني shattering the pieces around the rock on the surface. So it ends up with having this shape, and so on. Each period of time, the shape, the layer, more layers are demolished. Another type of mechanical weathering is the unloading and exfoliation. This is the normal shape. I have this magma inside stored at this location, but due to the effect of weathering, the sedimented soil on top is eroded and ends up having something like this. This is what remained from the sedimentary rock, and of course, because this is an igneous rock, it is stronger, so it stayed in place. But due to the effect of the unloading that happened to this rock, so also the surface layers are going to be exfoliated, as if you are taking layers out of it, layer by layer, till it is eroded itself. Another type of mechanical weathering is called biological activities. Biological activities, it is either because of small animals or because of roots of plants. These are examples that show you what is happening. Chemical weathering. Chemical weathering in some types of rock, they are affected by the effect of water. Water, with time, it changes to be a little bit acidic, minor acidity, but it is enough to initiate a reaction between water and the rock, and to cause the rock to be weathered from inside, or disintegrated from inside, so resulting in caves and so on, and sinkholes. Caves are what is happening inside. Sinkholes is the effect, the surface effect of the surface of the cave falling inside. If I have a big cave like this, and the surface collapses, it will result in a sinkhole. So this is a good photo summarizing what is happening in chemical weathering. How to prevent weathering? We said this. We said this that it's not always that we need to prevent the weathering. We said it when we were discussing each one, so we don't have to repeat it again. That we don't need to prevent all types of weathering. So we'll go directly to the geologic structures of the Earth. We said that geologic structures of the Earth are primary tectonic and secondary, primary non-tectonic and secondary tectonic. We said it before. What are the geologic structures? Geologic structures are either the normal horizontal beds, something like this, or graded beds. They are horizontal beds, but inside the bed they are graded. The big pieces are below, the small pieces are on top of each layer. Another type of geologic structure, cross beds. Cross beds is that I have layers going in this direction, inclined direction, but inside I have other layers going in the opposite direction, inclined also. So this is called cross beds because they are beds crossing each other. I have something called curved beds. You remember, you have studied anticline and syncline. These are curved beds. So this is a type of bed that is curved upward. It may be curved downward as well. Geologic structure, we have something called graben. Graben is more or less a fault, or you can call it a double fault. It is a fault happening here and another fault happening in the opposite direction. So this piece falls down and these pieces on the right and left stay in place. Dike is just a crack in the top layer of the of say a sedimentary rock, and this crack is filled with molten material from an igneous rock below, or any material from a layer below. So this is this layer, this dike belongs to the layer that is below the ground. It just goes up. Rock outcrop is part of the layers, but it is just outside the earth. I can see it on top of the earth. So it is important because it helped me to know what is below and the direction and the inclination of this rock without the need to do any type of investigation or excavation. So it helps in site investigation. It is very important. This is the shape of a fold. A fold is something like this, rock layers being bent like this. Types of fold, we said that we have anticline or syncline. Anticline is curved up, syncline is curved down. If we say where is the older rock, of course the older rock, this was the older rock, here this was the older rock. So the older rock here is inside and the older rock here is outside. This is just for comparison. Fault. This was the original formation. It happened that due to some type of forces, these layers fall a little bit down. So this point happened to be this point. It moved like this. So this is a fault. Another type of fault, and we said that this is a graben. It is a double fault. So a graben is a double fault because I have a fault in the two opposite directions. This is the geologic time scale that we have just seen before, and this leads us to the unconformity. Unconformity. It is it first, it have four periods. The first period is called deposition. This is the normal formation. I have layers A, B, C, D, and so on. Horizontal layers are formed. Then, due to forces on these deposited layers, they are deformed. When they are deformed, I have different type. They are not horizontal anymore. They change in shape. Then there is a period of erosion. Take a line here, something like this, and everything on top here is eroded. So it is not there. So it is the other phase is called, the third phase is called erosion. The fourth phase is called renewed deposition, new deposition, because once this is eroded, new layers are deposited on the top. So this line now is not similar to this line. This line is a normal separation line between two layers deposited simultaneously after each other. But Here, this is a line separate, we can say that it represents a gap in time. I don't here I have this belongs to a different periods of time, and these are new periods of time, so it is a completely different line of separation. This is examples for unconformity in nature. This is the unconformity line here. This is the unconformity line here also. And this is a summary for all types of unconformity. Unconformity have 4 types: nonconformity, angular unconformity, disconformity, paraconformity. Nonconformity, it means that sedimentary rock, but below is non-sedimentary rock. Disconformity is sedimentary rock on top and sedimentary rock at the bottom. Both are sedimentary. Angular unconformity, it is sedimentary rock, but the direction of the layers changes. Paraconformity, it is similar to this one, but the difference is that this line of unconformity is a parallel line, is a horizontal line. So this may be the line of unconformity. So this is very, very difficult to trace during site investigation or in nature, because I will find a horizontal line, but it only separates between 2 types of rock that are far away in time between each other. So here it needs a very specialized one in geology to tell me where is the paraconformity line. So this is example of unconformity. It is an example similar to this angular unconformity. It is called the Sicker Point in UK, in Scotland. These are inclined layers followed by another type with a completely different period of time. It was discovered by a scientist called Hutton, and he found it in 1788. It is very important because it proves this unconformity theory. Another example of unconformity is found in United States. It's called the Grand Canyon unconformity. The Grand Canyon unconformity is very, very rich because it includes lots of unconformity. This type here is nonconformity because this type of rock is igneous and this is sedimentary. So it separates, nonconformity separates between igneous and sedimentary. Here it is sedimentary and here it is sedimentary, but this is inclined and this is horizontal. So it is called angular unconformity. Here it separates between 2 types, but they are both horizontal, so it is called disconformity. So you have lots of features that you can study. So the Grand Canyon is very important for this. The final part and the very important part is why we are studying all of this. Now you can say that we ended up the revision, but why we are studying? What is the link between geotechnical engineering and geology? The link between both is what we said in our revision lecture now, and to prove it on site, we use site investigation. Site investigation, I drill boreholes. These, of course, test pits are not important for geology, but test pits are important just for geotechnical engineering. But boreholes, especially if I have deep boreholes, then boreholes will go below far below the surface of the earth. I will see different types of layer. How can I anticipate how these layers move? Are these layers horizontal, vertical? Are there curved layers? Are there folds? Everything that we have studied is represented can be represented by these boreholes together. Rocks. The rock cycle is very, very important. I have to know the types of rock. I have igneous rock, metamorphic rock, and sedimentary rock. These three types of rock can be weathered or eroded to end up having sediments. So if I have these three types of rock, then the three of them can be transferred into sediments. But in between igneous, metamorphic, and sedimentary, I also have movement. Igneous can be metamorphic by the effect of heat and pressure. Sedimentary can be metamorphic by the effect of heat and pressure. So this is the internal movement between the three, and the three can move to be just normal sediments by weathering and erosion. If these sediments are compacted and cemented together, they again change to be sedimentary rock. What about metamorphic rock and igneous rock? Metamorphic rock and igneous rock, if they are affected by very strong heat, they melt to be magma, and this magma come out in volcanoes to be igneous rock, and so on. So this is how all types of rock interchange between each other. What do we do in site investigation? This is important. Suppose I have a site investigation like this. I have this borehole and the other borehole. Both boreholes are more or less identical. Does this mean that if I have two identical boreholes, does this mean that what is in between is similar? No. Look at this case of a dike. I have borehole here and another borehole here. Both boreholes are more or less similar, but in between I have a dike. So this I have. How can I know this? Either I perform another borehole in between, or use seismic waves to discover what is in between. And of course, study geology. If I study geology, then I know what to expect. If I have a borehole here and another borehole here, and I have an anticline. In an anticline, this borehole and this borehole at these two specific locations, they are similar. Someone would take horizontal lines to join these boreholes, and it will be completely wrong. So I need to know that this is an anticline or maybe a syncline. If I have erosion, I will take here a borehole here and another borehole here and another borehole here. Imagine that I don't take this intermediate borehole. I just take this one and this one. Of course, if I take these two boreholes, I will not discover that there is in between another type of rock. Case of graben or fault, but if I have these boreholes, then I need to have the experience to judge if there is a fault inside or a double fault, a graben inside. A completely big problem. If I have symmetric fold, it is a minor problem. Asymmetric fold, it is more or less a less problem. Overfold, increasing in problem. Recumbent fold, it is a mess. It will be very difficult for people to judge this borehole unless they know geology, because it will give them as if they have horizontal layer covering the whole site, though it is just a fold that has been recumbent and changed in shape. This is something new. If I have a site investigation here, these are boreholes, borehole 1, 2, 3, and 4. can you expect where is the location of a fault if I just give you the boreholes? Usually in real life we should do this from any site. It is very I would be considered a very not a clever geotechnical engineer if I have boreholes in an area where I have a fault, I do not discover it. It's a complete disaster for me, because this will result in big problems for the building. Imagine that this is the location of the fault. You have a fault here, and these are the boreholes. Of course, if I have a fault here, it means that part of the soil has, part of the rock has fallen down a little bit. So borehole 3, 5, and 6 will be shifted below. Borehole 1, 2, and 4 will be in place. So we can look at this, or just it's not given, but imagine that you take a borehole 2 and borehole 3. You will find that the items found in borehole 2 are the same found in borehole 3, but at borehole 3 they are found a little bit below the level at borehole 2. It means that there is an expected fault in between. The same, if I take borehole 4 and borehole 5, I will find this more or less the same items here, the same as here, but in borehole 5 they are shifted below. So I expect the fault to be here, and so on. Between borehole 2 and borehole 5, I will also find a shift. Then I can expect the location of the fault to be there. If I just join these lines together, then this is the expected location of the fault that is passing by this site. What should I do? If it is an active fault, I should leave the site, go to another site. If it is an inactive fault, then I will just take a safe zone away from this location and start putting my building. It is not active, it is not moving, but maybe it would move a little bit. So I will just take a zone for safety, and I'm not allowed to put any buildings. Say I would take a zone like this here and a zone like this here, and all of this area I cannot put my buildings on top of it. I can put my building here, I can put my building there. It is okay. So now what should I do in a site investigation? I will have just boreholes. To do a correct site investigation, then I should join this site investigation with the following points as needed. Study geology. Of course, this should be in any site investigation. If you are doing a site investigation and you don't know about geology, it's a problem. Use additional boreholes in between. Usually when I come to a site investigation and I get this borehole and I get another borehole and I found that there is something different, very big difference between both, so I will need to add one borehole in between to study what is this difference. So I use additional boreholes if needed, if I find discrepancy between boreholes. Use geophysical methods. I can use geophysical methods always, but it is important if I find differences between boreholes, so I need to study what is in between and how layers are moving from one borehole to another. So this is geophysical methods. Last thing, inspect the surface for possible features. As we said, there may be some outcrops, there may be some sinkholes, there may be something that would tell me what is below by seeing what is on top. This is a summary of what we can do for site investigation. This ends up this summary and review lecture. I think now you can go to your exams. You have all the knowledge that help you to answer all questions and correct, and I hope so, inshallah. Thank you, and see you in the exams.